Back, we have been talking about scan testing. So, any modern day VLSI circuit, right, as I mentioned earlier also, will basically be a sequential circuit, right. And often we use what is called as core based design. Right. So, there will be IP cores. Remember, IP means intellectual property. So, intellectual property. So, companies sell these intellectual properties, for example, microprocessor core, right. There could be a memory, and there may be various peripherals, USB controller, right, Bluetooth controller, so many different peripherals controllers may be integrated. So, as you can see, each of these is a sequential circuit. Memories of course are they are slightly different, right. There may also be some analog components, right, sometimes especially in microcontroller based systems. Okay. So, when you look at microcontroller based systems, they are very likely to contain things like op amps. They may have A to D converters, D to A converters, some memory also like RAM. They may also have flash memory, and then there may be some peripherals like USB controller, etc. So, this is a digital block, sequential. These are also typically sequential circuits, digital. So, when you integrate a number of IPs like this, right. So, typically what is likely to happen is each digital block, so let us call this B1, B1 is a digital block. And it may have a number of flops. And there may be a scan chain. Okay, this is known as a scan chain, maybe I have never used that terminology before. So, scan chain refers to this is a scan input pin, scan output pin, and remember how there is a shift register that gets implemented when the scan enable is high, right. This thing is known as a scan chain. So, in this example I have shown one scan chain, okay, with one scan input and one scan output. So, you could write the same thing somewhat like this. There is a block 1 and it has a scan in and scan out, right, and of course clock, etc., reset clock. So, there may be another block similar. So, if you have a number of these digital blocks, okay, you may have the ability to sort of, maybe you can connect the scan in of block 2 to scan out of block 1. So, this way there will be one single big scan chain. If you want to leave it as it is, that is also fine. Okay. Then there will be two scan chains. So, one will be scan in, scan out, scan in, scan out. So, it possibly is called scan out. Okay. As a matter of fact, in the digital block 1, we may not want to connect all the scan chains into one single scan. We may not want to connect all the scan flops into a single scan chain. So, sometimes it may make sense to have one scan chain like this and maybe another scan chain like this. Okay. So, the block B1 may look like this. So, there are two scan chains. And the same is true for block B2. So, it is up to the designer who integrates these blocks to decide how the test architecture will be at the top level. Okay. So, at the top level, you may integrate a number of blocks, let us say B1, B2, B3, B4, okay, and each of them may have many scan chains. So, you can wonder why there will be multiple scan chains. Okay. The reason for that is, as I explained to you, it takes a long time to initialize the scan chains. So, as I explained to you, if I have a single test vector, you will need n clock cycles to scan in the state and then one to capture the next state, right, and then another n to scan out the next state. Okay. So, this is a long time, right. So, it may be worthwhile to break the single long chain into multiple scan chains, right, and when we do that, we try to balance them out. Okay. See, suppose there are 1500 flip flops. Okay. We could have, it is very common to have 8 scan chains, 4 scan chains, 16 scan chains and so on. Okay. When you have, let us say, 16 scan chains, okay, each scan chain will have approximately 100 flops. Okay. So, we try to balance them as far as possible. Okay. In this example, we can't exactly balance, okay, because 1500 is not divisible by 16. Okay. So, we may have some slightly longer scan chains, okay, but we try to balance the lengths of the scan chains. So, there is what is known as automatic test equipment. I may have used this term before, automatic test equipment. This stores the test patterns. So, they may be scan test patterns. So, remember what a scan test pattern will have to store. We have to store 2n bits, right, at least 2n bits. In fact, there will be more. See, if you have a primary input, primary output, let us assume that this is m bits and let us say this is q bits, and then there is a state register of n bits. So, test vector will consist of m plus n bits input and q plus n bits output. So, you will have total m plus q plus 2n bits for one vector. So, let us make up some numbers. Imagine that we have 5000 patterns, and imagine that we have 100 inputs, and n is also, let us say, 100. No, n may be larger, n may be 1000, and q may be, let us say, also 100. So, you will realize that one vector will correspond to approximately 200 plus 1000, 2000, so 2200 bits. And if you have 5000 patterns, it will correspond to 2200 multiplied by 5000. Okay. So, those many bits. So, as you can see, this is quite a large number of bits. Okay. It is a lot of storage, right. In fact, this is a modest example. The modern day chips can be much larger. The number of vectors may be much larger, and the number of flops may be much larger. So, you will see that the storage, right, that is required, it has to be stored on some hard disk. Okay. And see, when you apply the test vector, so here is a chip. See, we have to apply the scan tests at a much faster rate, right. It can't afford to read one test vector at a time from the disk, and then, so it possibly will read many of them into a buffer which is on chip memory, which will be fast, and then it will supply the chip with the test data at a much faster clock. Okay. So, as a result, it requires a lot of memory, on chip memory, and this memory has to be fast memory. Okay. So, ATE in a way must be faster than the chip. Okay. So, ATE must operate at a much higher speed than the chip itself, otherwise the testing may not be correct, right. So, that is the reason why ATE can be expensive. Okay. We have already mentioned this, that they cost millions of dollars. That is because the kind of memory that is used, they may use expensive high speed memories in order to achieve the bandwidth that is required. Bandwidth means it means how many bits can you supply per second. Okay. So, we may require a very large number of bits must be sent in every clock cycle to the chip, right, and as a result the memory bandwidth of this ATE must be high. So, that is the reason why ATEs can be quite expensive, right. And they can supply the number of scan chains that they feed, okay, can vary from 1, 2, 4, 8, 16, 32 and so on. So, the number of scan chains, some people try to call it scan channels, okay, can be 1, 2, 4, 8 etc. It may go up to 32 or something like that. The higher end testers will have more scan channels. The low end testers will have fewer number of scan channels, right. So, as I was explaining, right, at the top level it is the responsibility of the designer to interconnect these scan chains. So, in one of them there may be 8, in another one there may be 16, in another one there may be 4 etc., etc. So, it is the job of the designer, and the designer is sometimes called as a design for test engineer. So, he is a DFT engineer. DFT, as I mentioned to you, means design for test. We have so far seen the word DFT in two contexts. One where I mentioned that you can insert test points. See, that is also a place where you are modifying the design, okay, for the sake of testing, right. When the observability is poor, we may want to add observability points. When the controllability is poor, we add control points, right. In the same way, we can add scan chains. So, the engineer who is responsible for modifying the design to add test points, scan chains, etc., that engineer is typically called as a DFT engineer, design for test. So, the DFT engineer will have to add the extra logic that may be required to steer the test data to and from the blocks. So, at the top level, you may have made room for maybe 16 scan chains, right, 16 scan ins and 16 scan outs, and the blocks may or may not have that many. Okay, some of them may have more. For example, this may have 4 scan chains, this may have 8 scan chains, this may have 16 scan chains, and this may have 32 scan chains. So, you have to architect the testing, you have to decide the sequence in which you will go and test all these blocks, okay, and how these scan chains will be connected. Okay. So, some additional test routing logic may have to be added, so that the scan information can be sent to the blocks and the information from the blocks can be routed back to the scan chains and so on. Okay. So, the more scan chains there are, the more expensive the ATE will be. Okay. So, it may be possible during development when the chip is being designed, right, we may not have access to an expensive tester. Okay. The tester may be even located in a different place altogether. So, there may be another country where the manufacturing is happening, okay, and the design is happening somewhere here. Okay. So, they may not have access to an expensive tester at this stage. So, they may develop all the tests on a low cost tester. Okay, which has a few scan chains, maybe it has only up to 3 up to 4 scan chains, whereas the larger tester may have access to a larger number of scan chains. So, the DFT engineer has to plan for how to test it on the low cost tester during development, and then later migrate to a larger tester with more scan chains. Okay. So, all this is generally the work of DFT engineers. Okay. So, DFT is an important aspect in the VLSI design flow. Okay. So, the DFT engineers are part of they work closely with the design team, right. And as I told you, typical things that we have to worry about is area. Okay, if you add too much DFT logic, it increases the area, and as a result it increases the cost. Then what performance impact is it having on the design? Okay, if the design is expected to work at 500 megahertz, in the presence of DFT it may not work at 500 megahertz. So, that can be a problem. Then there is the power, right. The DFT logic will consume extra power, okay, and extra pins. Okay. See, I told you that sometimes you may want to have up to 32 scan chains, right. Now, 32 scan chains means you see 32 scan inputs, then 32 scan outputs, then there is 32 scan enables. See, this is a lot of pins, right. So, people will frown and say, we can't possibly give you that many extra pins, right, because pins are expensive. Okay. When you add more pins, you will have to go to the next level package, okay, and the more pins in the package, the more expensive the package becomes. Okay. So, this is prohibitive. So, what people have to do is to multiplex the scan inputs and scan outputs and scan enables with functional pins. So, because during the test mode we do not really go and use the functionality of the chip. So, the pins which are meant for functional inputs and outputs we could multiplex. Okay. So, this is called as pin multiplexing. So, a pin mux will multiplex between the functional pin and the DFT pin. When I say DFT pin, I mean things like scan in, scan out, scan enable. Okay. So, that is also an important aspect.